So today we are starting now into looking at maxima and minima, both absolute and local. And so whenever I'm trying to figure out where the maxima and minima are, I always start with the absolute ones first. Because once we've dealt with the absolute ones, then the locals can just be what's left. Because if it's absolute, it's not local. We're kind of ruling that out. So let's start by looking for an absolute maximum. Where's the absolute maximum of this graph at? F. Yeah, F would work. We have an absolute max. If we can actually get this thing to write. Absolute maximum would be F. But you notice that's not the only possible answer, right? F is an absolute maximum, but so is B. And so the absolute maximum would be both F and B in this case. What about the absolute minimum? Where's the absolute minimum? E. Because these absolute maxima and minima, they're the points that reach the highest possible of every on the graph. So you notice that E down here, that's as low as any point goes, so that must be the minimum. But both B and F reach the highest possible. And so there can be multiple, but if there are multiple, it's because they reach the exact same height. All right, now what about the rest of them? A, C, and D. Well, then we get into the local maxima and minima. So the local maximums. Where do we have a local maximum here? Well, you notice that basically what the local maximum is you're saying that as I'm looking at my graph, as I follow it from the left side, it stops going up at this point. And as I follow it from the right side, it stops going up at this point. It's just B that I just illustrated with, that was an absolute maximum. Where do I see that same behavior that's not at B? At D, right? Because from the left side it's increasing and from the right side it's increasing. And so then a local maximum would be at D. Same kind of thing for a local minimum. As I'm coming from the left side and from the right side, where do they both stop going down? It's kind of similar to the idea of limits, actually, in a way, where we're seeing where does it keep going down. In this case, we have a local minimum at, well, we can see it at C. What about A? Is A local minimum? No, it's not. Because as we approach that point from the right-hand side, yes, we keep going down and it stops going down at point A. However, from the left-hand side, there is no left-hand side. So it's not going down from the left-hand side as well in order to make that a local minimum. So notice then a distinction. For the absolute maximum or minimum, an endpoint was possible because it's just talking about this is the highest the graph ever reaches. But when it comes to the local maximum and minimum, there it cannot be an endpoint. You might want to make note of that idea into your notes just so that you remember that, because that's one of those little subtleties, and today we got to get into some subtleties along the way. All right, so now we're going to see how those ideas apply to this graph. And again, I'm going to start by looking at my absolute values. And so I'll look for where's the absolute maximum and where's the absolute minimum. And then we'll go into the local maxima and minima, if there are any. There's no guarantee there even are any. We'll see. All right, so for the absolute, where's the absolute maximum in this graph? Yep, looks like it's happening right here. So yes, that is D there. So the absolute maximum for this graph is at D, because I'm just looking at my graph and looking to see what's the highest point it ever reaches, and that's just the highest it ever goes. All right, what about the absolute minimum? Where's the absolute minimum? Well, we're probably looking at two possibilities here. It could be here or it could be here. Now, A is lower, but A is an endpoint. Again, bringing it back to what we talked about earlier, can an endpoint be an absolute minimum? Yes, it can. And so then our absolute minimum would be A. All right, local maxima and minima. Let's just go through it one by one from here. Let's see what they all check out to be. Let's see if B. Is B a local maximum? Because you notice it's topping out there, so that's why I automatically go to maximum. Is it? Yes, it is. And so B would be a local maximum. What about C? It looks like it's bottoming out there. Is C a local minimum? It kind of looks different from the other points, right? It's not rounded there. It comes to a point. It's a corner on the graph. Can we still say it's a minimum? Yes, we can, because it's still approaching it from both sides heading down. So C is a local minimum. D, is that a local maximum? No. It was our absolute maximum. So it's not also a local one, it's just the absolute. All right, and then for C, is that a local minimum? I'm sorry, E. Is E? Yes, it is. E is, in fact, a local minimum. Now, we didn't talk about this point out here. If the graph ended there, so like if we actually had a point there, would that point be a local maximum? No, it wouldn't. Because remember, a local maximum or minimum can't be at an endpoint, because it has to be approaching it from both sides. Now, having gone through those examples, we have one last example, just finding out where those local maxima and minima are. And it's going to be this one. And this one, well, it brings up all sorts of little subtleties, and it allows us to get into a lot of little detail-y stuff. All right, so let's go ahead and take a look then at these. And again, I always like to start with the absolute maxima and minima first. So the absolute maximum, where would the absolute maximum of this graph be? Well, and this is where things get interesting. I did say that this one's going to offer all sorts of trickiness here. In case you're trying to follow it, there's where our origin is. But it looks like our maximum would be up here, right? Because this is the highest point it's going to. There's nothing higher. And so it looks like we'd be saying it's at x equals 0. But it's not. Because when x is 0, what is y? Well, y is actually 3 here, but of course that's not really the point we're looking at, right? Okay, so let's go ahead and jump up. Let's go ahead and go up to there. It looks like it's approaching 5, right? Well, it is approaching 5. But what is the actual maximum that we're achieving then? Because we aren't actually hitting 5. We're just approaching 5. Now, that might make you tempted to think, okay, well then it's 4.9 repeating. But 4.9 repeating really represents a value that we're approaching still. You can never actually reach that value even still, because no matter how close you get to 5, you can still get that little bit closer, right? And so for this absolute maximum, it's close to 5, but since we cannot actually reach it, we cannot actually state what that maximum is, we actually can't give an absolute maximum for this graph. There is none, technically speaking. Yeah, this one brings in some trickiness for us. All right, next up, absolute minimum. Let's look for that absolute minimum. I'm looking to see how low does this graph go. It looks like this is as low as it's going to go. Can I then actually use this as an absolute minimum point? Yes, we can. And so then I would say that the absolute minimum is going to be where x equals 4. Or for giving it as a y value 1, but I'm just worried about where the x's are at the moment, since that's the way we've been dealing with the other ones. All right, now let's go to the local maxima and minima. And And for this, there's just a lot of stuff going on in this graph, so I'm just going to go left to right here. So, first point I encounter right here. Is this a local maximum or minimum? Well, it's higher than it is there, so is that a local maximum? No. Because remember, for it to be a local maximum, it has to be getting higher from both sides. I would have to have some graph on the left-hand side there where it was also increasing. But I don't have that. And so that's nothing to us. Okay, so then let's go to this one then. I'm going down as I approach it. Does that make this point a local minimum? Well, is it going down to that point from both sides? No. Therefore, it's not anything again. This point is not a local minimum. Okay, up here now. Is this then a local maximum? No, same reason, because we're not approaching it from both sides. We're not going up to that point from both sides. Okay, so then we're still going down from there. I hit this point. I'm going down from the left. I'm going down from the right. Does that mean that the local minimum is here at x equals 2? This, again, is a very tricky one. The answer is that yes, there is actually a local minimum at x equals 2. It's just that that local minimum is not up here where it's approaching. The local minimum is actually this point here. If I were given the coordinates of that minimum, it would be 2, 2. So it is where x equals 2, but it's the y being 2. It's not just up around here. All right, continuing on from there. Let's go follow our graph. We're going up, and then I stop going up. Check it from this side. I'm going up, I stop going up. Same point. Okay, this is good. So then, is this a local maximum? Yes, it is. Thankfully, that one's nice and simple and straightforward. It's just topping out there. So that's at an x value of 3. So I've got a maximum at x equals 3. Okay, follow that down, and I end up at this point. Is this a local minimum? No. Because it was the absolute minimum. We already used it for the absolute. And so that's why I would not then identify it as a local minimum. All right, and finally, if I follow that up, yes, I do end up with another one right there. So I got a local maximum there. And this point here at 7, where x equals 7, is that anything to us? Nope. Because an endpoint could be an absolute max or min, but not a local one. And it's not an absolute max or min. Then this actually lets us summarize a little bit of what we've already observed in this idea of the extreme value theorem. So this now needs to go into your notes, and then we'll take a look at how it applies to those graphs below. Now, notice, let's start by taking a look at the last graph. Remember, in the last graph, it did not have an absolute maximum value. The extreme value theorem tells us how we can know there is one. So why doesn't this apply to that last graph? Well, first of all, in the last graph, was it on a closed interval? Well, on the left side it was a solid dot, on the right side it was a solid dot. And there were no actual gaps in between. So, yeah, it was a closed interval. But was it continuous? No. And the fact that it was not continuous actually ended up causing us the trouble. As you take a look at the graphs that we can see down below here as examples, these top 3 graphs up here, each of those represents a situation where actually the extreme value theorem will apply. And so you'll notice that for each of those, we've even labeled on there an absolute minimum wherever D is labeled, and an absolute maximum wherever you see C labeled, to prove that there actually is one between them. The basic idea here is that as long as it's continuous, there has to be one. And notice why it has to be a closed interval. If this was an open dot at the end, then all of a sudden there's a possibility, actually I could use this one as example over here, then in that kind of a case we wouldn't actually reach that value, so there wouldn't actually be a minimum in that kind of case, because it wouldn't be a closed interval. Now down below we see some graphs that fail the extreme value theorem because, well, both of these cases they're not continuous. Because we have a discontinuity here, and that ends up creating the situation where there is no absolute maximum in that particular case, because this is an open circle. And then for the second one, we have that asymptote in between, creating a discontinuity. And so just remember what some of those discontinuities are as well as we go forward. Now, coming back to this graph that we looked at earlier, let's think about what's happening about the derivative at each of the local maximums and minimums. Okay, so our first local maximum or minimum was here at B. What is the derivative here at B? It's 0. Because remember, derivative is slope of the tangent line. If I drew the tangent line in there, notice it would be horizontal. So yeah, there, my derivative is 0. Okay, what about at C? What would the derivative be at C? Well, actually there we got a little bit of a problem. It's been a little while since we've had to deal with this question, but there's actually points, remember, where we cannot take the derivative, and one of those times is at a corner point. Because we could make arguments for the slope of the tangent line being all sorts of different things here. It's because it's a corner. And so the derivative there would actually be undefined at point C. Okay, what about D? What would the derivative be at D? It's up at our top here. Our derivative there would be 0. And what about at E? That minimum. Well, notice there our derivative is 0. But we want to be able to have a rule that kind of brings our attention to when do we know that there's something important happening in this graph. And it could even be something that we could apply to this point, as well as this one where it was undefined. Those points, they tend to be where maxima and minima are, but there's also going to be some other variations we'll be taking a look at. All of those end up being what we call critical numbers. And so a critical number will always happen when our derivative is either 0 or when the derivative doesn't exist. So get this down to your notes now. All right, and as you make note of these, just something to look out for is that this second statement here, the one that's labeled 7, why 7? Because that's the way the book had labeled it, so we don't worry about it. It's saying that if F has a local maximum or minimum at C, then C is a critical number automatically. The reason for that is because a local maximum or minimum will always happen either where our derivative is 0 or because the derivative doesn't exist. So a local maximum or minimum must be one of those two scenarios, and therefore, since it must be one of those two scenarios, that also qualifies it as a critical number. It's just being a little detail-y there. But we will be seeing some other critical numbers that are not maxima or minima as we go forward. So that's the distinction. All right, so we're bringing it back then to this graph again, same one you saw earlier. But now thinking about what are the derivatives at the local maximums and minimums. Well, we already know that they should either be 0 or not exist, right? So let's take a look here. We found earlier a local minimum right here. Okay, what's the derivative at this point? Doesn't exist. The derivative here would be 0. It's got to be continuous through there for us to be able to find the derivative. At this point, our derivative would not exist. Because remember, it cannot exist at a corner. And at this local maximum, it's nice, smooth, and continuous. So yes, that would be actually 0, again, for what the derivative would be. Remember that these were the different ways that we could end up with a graph or a point that was not differentiable. So it can happen at corners, discontinuities. Remember, we have 3 different kinds of discontinuities: jumps, holes, and asymptotes. And it can also happen if we have a vertical tangent along the way.